All right, in section 4.3 and 4.5, we're going to look at an application of derivatives called optimization. Optimization is just the process of finding the best answer to a modeling scenario. It might be maximizing volume. It might be minimizing perimeter or minimizing cost, something like that. So in example number 1, first of all, they start and say, we're going to find the maximum volume, but oftentimes that's not a given piece of information and it's embedded within the problem scenario, so you have to figure out what you are maximizing or minimizing. So in this problem, we have an open box having a square base that's to be constructed from 108 inches of material, square inches of material. What dimensions will produce a box with the maximum volume? So we've got some steps written out here. In step 1, we want to state the quantity that we are trying to optimize. So our goal is to maximize the volume. We want to be able to fit as much as possible into this box. All right, second step is to make a sketch. Okay, you may or may not have done a problem like this before where you, I'm going to do an example here where you essentially have a piece of material. So here's this rectangular piece of material. I don't know if the material is square to start with or not, but I know it's 108 square inches. And here would be an example of if I cut out the corners of this material, and if I fold the edges up, so I'm folding this up and folding this up to create some sort of open-topped box. Okay, so my picture might look like this, where these corners are going to get cut out and folded up. All right, and obviously the height of the box is going to be the same all the way around. Okay, so this distance is h. I'll call it for height. Now in my picture, it looks like I have a rectangular base, and I obviously do. But with this question, they want the base to be square. So I'm just going to label each of these dimensions here x. So the length and the width are both x, even though my picture is not drawn, so it's going to turn out to be a square base. Okay, now third step is to write a formula for the quantity that we want to optimize. So our goal is to write a formula for volume. All right, according to my picture, I know volume is going to equal x times x, that's like length and width of the base, times the height. So that's my volume. In step 4, it says we would like to have this volume formula in terms of a single variable. Okay, so that means I need to use a secondary equation to rewrite this formula. So I'll say I only want it in terms of x. So how could I find an expression for h? Well, I'm going to use the fact that they've told us that the material has an area of 108 square inches. Okay, and according to my picture that is labeled, I know the dimensions of this 108 square inches is x plus 2h by x plus 2h. Okay, so that means my area is equal to x plus 2h squared, which is 108 inches. Okay, I need to solve for h so that I can substitute the h value into the volume equation. All right, so let's solve. That means x plus 2h is equal to the square root of 108. Okay, 108 is actually equal to 36 times 3. And so that's 6, the square root of 3. All right, 2h is going to equal 6 plus the square root of 3 minus x. And if I divide by divide by 2, I'm going to get 3, the square root of 3, minus 1/2 x. So now I know a value for h. So I can write my volume function in terms of x. It will be x squared times 3 root 3 minus 1/2 x. Okay. Sometimes modeling the function is the most difficult part. All right, so that's from step 4, our equation. In step 5, it says we want to take the derivative. Because remember, if we want to find a maximum or a minimum, we want to find where our derivative has critical points. So take the derivative, and then in step 6, we'll find the critical numbers and decide where we have maxes or mins. So v prime, let's do the product rule. So that's x squared times negative 1/2 plus 2x times 3 root 3 minus 1/2 x. Okay, I'm going to simplify this a little bit. I have negative 1/2 x squared plus 6 root 3x minus x squared. And I'm only distributing this so that I can combine my x squared terms. And so I'm going to have negative 3/2 x squared plus 6 root 3 x. All right. And I'm going to go a step further and get a common denominator and also factor out an x. So I have x, negative 3x plus 12 root 3 all over 2. So I gave the second term a common denominator of 2, changing the 6 to a 12. I also pulled out a factor of x, so it's in factored form. All right, so the reason why I did that is because in step 6, I want to find the critical numbers. So I need to know when v prime is equal to 0. So that means x times negative 3, well, I guess I could have pulled out a negative 3 as well. X plus 12 root 3 is equal to 0. So that means x is equal to 0. That's a critical number. Or x is equal to 4 root 3. So that was negative 12 root 3 divided by negative 3. Okay, so there are my two critical numbers. Okay, in step 7, let's take a look some more. It says, throw out the values that fall outside the domain. So what is the domain? So thinking back to our picture, I'm going to go back to that picture. Is it possible that x could be 0? No, that's not possible, right? We have to have an x value greater than 0. So in our critical numbers, we'd actually throw this number out. X is not allowed to be 0, but I'm going to go ahead and in step 7, I'm going to take a look at our critical numbers and decide if they belong to extrema that are going to be maximum or minimum. So I'm going to put 0 on here, just saying, 0 is my end point interval for the domain. I can't have it. And 4 square root of 3 is a 0 of my derivative, so it's a critical point. Okay, taking a look at the numerator of our derivative, this is a negative quadratic. Okay, that means that the derivative is shaped like this. That means this is a negative y value, this is a positive y value, and to the left would be negative y values for my derivative, even though I'm not really looking at values less than 0. Okay, but what that means is that my function, my volume function, is increasing from 0 to 4.3 for square root of 3, and then decreasing beyond for the square root of 3. Therefore, when x is 4 the square root of 3, I must find a maximum volume. All right, so in step 7, establish whether or not the critical numbers correspond to local extrema. Be sure you identify whether you have a max or a min. Okay, and the reason why you want to make sure you identify is that you don't want to minimize, don't want to find out you found a minimum when you're trying to maximize, or vice versa. Okay, so in step 7, I'm going to say v prime changes sign from positive to negative at x equals 4 the square root of 3. Therefore, volume is maximized when x equals 4 the square root of 3 inches and height. Okay, now I need to go back and say what was my height. And height is 3 root 3 minus 1/2 4 root 3. So that's 3 root 3 minus 2 root 3, or square root of 3. Okay, so it says in step 8, find the value of the quantity to be optimized at each of the relevant critical numbers and answer the original problem in words and units. Okay, so I have found only one critical point in question for the square root of 3, and the original question was, what dimensions will produce a box with maximum volume? Okay, and the dimensions are 4 the square root of 3 by 4 the square root of 3 by the square root of 3. Okay, it didn't ask for this, but you could also state the maximum volume therefore would be, that'd be 16 times 3, or 48 the square root of 3. 48 the square root of 3 inches cubed. Okay. That is the first example of optimization. We're going to look at the next 3 examples, example 2, 3, and 4, and I'll continue that in the next video.